Dear students of B.Tech first year, I am Dr. Arvind Parsai, Associate Professor of Mathematics in Engineering Science Humanity Department at Chamini Devi Group of Institution Indore. I want to teach you through this video lecture for solution of non-exact differential equation of order 1 and first degree by rule 3 and 4, and I also discuss the solution of differential equation of first order and high degree by using method number 1. So first of all, we understand what to mean by rule number 3 and rule number 4. So the first condition is same as for all the previous rules related to this solving non-exact differential equation. So when the equation of the type m dx plus n dy equal to 0 is not exact, and if the ratio of this del m upon del y minus del n upon del x upon capital N is a function of x only, then the integrating factor is e raised to integral of power f of x dx. Then we come to the rule number 4 is when the equation is of the type m dx plus n dy is equal to 0 is not exact, and if we come to find the ratio of del n by del x minus del m upon del y divided by capital M equal to if it is a function of y, say g of y, then integrating factor तब उसका समाकलन गुणांक जो होगा e की पावर में इंटीग्रल ऑफ g of y of dy. Let we understand this rule by examples. So our first example is solve the equation x square plus y square plus x of dx plus xy dy equal to 0. Then our first duty to check the exactness of this type of problems as on comparing the given equation with m dx plus n dy equal to 0, and therefore on comparing this we get the value of capital M and capital N. Then you differentiate m partially with respect to y, the derivative of m partially with respect to y, in this case x keeping constant, so first term having derivative 0, second term having function of y only, so its differential is 2 of y, and the third term is only x, so its term differentiation is 0. Then we come to the differentiation of capital N partially with respect to x by keeping y as constant, so is 1 into y, that is y. Hence the given equation we say that we observe that both the derivatives are not equal, that is the given equation is not exact. Now we concentrate rule number 3 as del by finding the ratio of this del m upon del y minus del n upon del x divided by n. So the value of this is 2y and the value of del n by del x is y, divided by n is xy. So what will be the remainder is y, numerator is y divided by xy, y is cancelled with this. If this gives to you 1 upon x, that is only the function of x, then in this case therefore the integrating factor is e raised to integral of fx dx, that is fx is 1 by x. So what will be the integral of 1 by x is log x, and e raised to log x, the answer is simply x. Therefore on multiplying in this way the given equation by this integrating factor, then it will reduce into automatically in exact form, that is you will get as x cube plus xy square plus x square of dx plus x square of y dy equal to 0 is an exact differential equation. Then you are ready to find this general solution here. So what will be the formula of its general solution is integral of m dx y keeping y as constant terms of n not containing x of dy equal to 0, just substituting the respective value in this equation or in this general formula of finding general solution as x cube plus xy square plus x square of dx, and the terms not having x, that is none of the terms having without x, so that's why there is only one term in capital N having x, so that's why the value number of terms is 0, so that is 0 times of dy equal to constant of integration. So please find the derivative of this first term is with respect to x, so x cube का different derivative is x power upon 4 plus x square y square upon 2 plus x cube upon 3, and this is the integration is y multiplied by 0, it gives to you simply x power upon 4 plus x square y square upon 2 plus x cube upon 3 equal to c, where c is the constant of integration. Now we come to see the another example here. For this, your first step is also to be common on comparing the given equation or to this pattern as m dx plus n dy equal to 0, and therefore you will find capital M and the capital N values here. M is equal to capital M equal to x y cube plus y, and capital N equal to 2 of x square y square plus x plus y raised to 4. Now on differentiating M partially with respect to y, this gives to you the differential of this with respect to y is 3x y square plus 1, and the differential of this with respect to x is 2 to the 4x y square plus 1 into 2 is 2. Therefore you will observe that both are not equal, that is the equation is not exact, hence you will find the value of the integrating factors by applying this rule number 4 as del n by del x minus del m upon del y divided by m equal to, so this difference and the ratio is gives to you 1 upon y simply, that is only function of y. Therefore the integrating factor is integral of g of y dy, that is 1 by y dy. Integral of this function is log of y, and that the base is e, that's why log function is eliminated, simply this gives to you y. Therefore now you are going to multiply the given equation by this integrating factor, then it will reduce into exact form of course, that is we get xy4 plus y square of dx plus 2 into x square y cube plus xy plus y5 of dy equal to 0. Hence we write the general solution of the given problem as by writing first the formula as we discussed in the previous example, integral of m dx plus terms having not having x containing x, and then equal to c as constant of integration here. So the value is xy4 plus y square of dx and 2 of y5 of dy equal to c. Now find the integral of this function as x2 of y4 upon 2 plus xy square upon 1 plus y raised to 6 upon 3 equal to c. So where c is the constant of integration. Now we concentrate through this lecture also as part 2 of this unit number 1 of M2 as introduction of differential equation of first order and higher degree, along with our first method of solving this category of problems. So the most general form of a differential equation of first order and of higher degree, say of nth degree, can be written as dy by dx of n plus a1 of xy dy by dx raised to n minus 1 plus a2 of xy dy raised to n minus 2, and so on when you are going to ahead. So you will get a term saving function of independent variable as x as independent, y as dependent variable, as constant term is n of xy equal to 0. Or this type of, whenever you see this type of higher degree problem, that is degree is greater than 1, then you will put into a shorthand notation by applying this small parametric techniques as p equal to dy by dx. You are putting everywhere, so this gives to you p raised to n of a1 of p raised to n minus 1, a2 of p raised to n minus 2 plus n minus 1 of p plus n equal to 0. So this is the general form of higher degree first order differential equation. or this can be also written in shorthand notation as capital F of xyp equal to 0. Now we concentrate first method of solving this category of problem is when the equation is solvable for p. So in this regard, if you are able to factorize this equation number 2.2 into linear factors in terms of p, so let me suppose those factors are p minus q1 of xy, p minus q2 of xy dot p minus qn of xy equal to 0. Why it is so? Break into n factors, because you are given nth degree problems. I take the general case of nth degree. That's why whenever you are having nth degree polynomial, then how many roots you are having n roots. So accordingly we assume here, suppose that these are the n factors of this equation number 2.2 here. Now just by equating each factor to 0, so one can find this equation by the method discussed in the previous part as how can you solve. So that's why your problem of high degree is reduced into first degree and order is already 1. So that's why we have a lot of method of solving first order and first degree ordinary differential equation, so you can apply accordingly. So let us assume that their solution to be fi of xy of ci equal to 0, where I equal to 1 to n. How many solution here in this way you are getting? Because you are having n factors, you are getting n solutions. Therefore, the general solution of equation 2.1 as the given equation can be expressed in a general form as follows: f1 of xy c, f2 of xy c, and dot fn of xy c equal to 0. Why we are taking the constant only 1? Because we know that if you are you're going to solve a differential equation, then of nth order, then its general solution involves n constant. If you are having first order differential equation, that's why its general solution involves only one constant. That's why I take C, where C is an arbitrary constant. So it can be checked that's why I discussed and I have written in our this and sentential forms. It can be checked that this sets of solution represented by 2.3 and 2.4 are identical, because the validity of 2.4 is equivalent to validity of 2.3 for at least one I with a suitable value of C, namely C equal to Ci. So let us concentrate an example on this topic as, say I given the number of this example as 2, so is y of dy by dx 4 raised to 2 plus x minus y dy by dx minus x equal to 0. So obviously first you rectify the problems. First you just the category of problem. Of course it is higher order 1 and degree is 2. That's why this is a question of first order and high degree. Whenever degree is greater than 1, it means it is a problem of higher degree problems. So first of all you will put into our standard pattern by applying a parameters as dy by dx equal to p. To solve, put p equal to dy by dx. So that's why hence the given equation can be written as yp square plus x minus y of p minus x equal to 0. Now our objective to factorize this. If it is easily possible to factorize or resolve into linear factor in terms of p, then it means that this type of question is solved by this method number 1. Otherwise we have the other options also that I will discuss in the next coming lecture here. So this equation is yp square plus xp minus p of y minus x equal to 0. Now you can take common and resolve into linear factors. So you are getting one factor is py plus x, another factor is p minus 1 equal to 0. Now by separating both the factors here, py plus x equal to 0 and p minus 1 equal to 0, and then by putting the original value of p here, just the objective of p is to reduce the given problem of high degree to first degree. So that's why we use these techniques here. Y of dy by dx equal to minus x, here dy by dx equal to 1. So just this part as separated the variables, you can write here y dy equal to minus x dx, and here also to be, because it is first order and first degree, so the first simplest method is variable separable methods here. So that's why dy equal to dx. Now both are in variable separable form, therefore on integrating both the equations, so first equation having the integration y square upon 2 minus x square upon 2 plus some constant of integration you also take here, let it be c, so and c by 2, and simply this x square and shifting to this side of these terms, so x square plus y square minus c equal to 0, and from here you will get y minus x minus c equal to 0. And now by combining these two independent solution together, you can write the general solution of given problem is just multiplying these two independent solution here, x square plus y square minus c, one part left side, and the left side part of second solution independent solution is y minus x minus c equal to 0, where c is the constant of integration here. Thank you very much.